Electrostatics is the study of stationary charges, where charge is strictly defined as the property of matter, that thing in matter, that causes it to experience a force when placed in an electric field. Now, we normally would just know charges as either being positive, which comes from a proton, or negative, which comes from an electron. And an electric field is a region in space around a charged object in which another charged object would experience a force, and we can show that with an electric field pattern that shows the region around this positive charge where other objects would experience a force, and the same with this pattern around the negatively charged object. What's important to see here is that charges are able to move. They're able to move from one object to another, and usually that is done through friction. It is also important to note here that it is only electrons that can move as a result of friction, as the protons, the positive charge, do not move, they stay where they are. And so when electrons move from one object to another, the charge moves with them. We can demonstrate how friction causes a transfer of electrons or a transfer of charge with a very simple setup that has a cloth, a piece of perspex, which is just any normal ruler, and some small pieces of paper. And what we can do is we can, by rubbing the perspex onto our cloth, what we will start to see, or what is happening here, is that we are transferring the electrons from the cloth onto the perspex, and as a result we are building up a positive charge on this perspex ruler. We can demonstrate that charge by bringing it close to some small, very light pieces of paper. You will see that before I even touch those paper pieces, that the pieces of paper start to move. This is as a result of the electric field that is built up around this, and then when they do touch, you will see that they are able to stick to the piece of perspex as a result of the charge buildup and the attraction between the negative charge that is built up on the perspex and the polarization of the pieces of paper. So what we've shown here is that through the friction between the perspex and the cloth, we have built up an excess of electrons that have been transferred from the cloth onto the perspex, which makes this perspex negatively charged. It also makes the cloth slightly more positively charged. And the fact that there is now a charge buildup on this piece of perspex means that it is able to attract the positive charges that are present in the pieces of paper, which causes this attraction that we have seen in this demonstration. Charge is the property of matter that causes it to experience a force when placed in an electric field. It has the symbol Q, and it is measured in coulombs, which can be abbreviated to a C. We would often say that charge is quantized, meaning that it comes in discrete units, or that there is a minimum amount of charge that is possible, and that is called the fundamental charge, which has a value of 1.6 times 10 to the minus 19 coulombs. This is also the charge that would be found on electrons and protons. So they have the fundamental charge. Obviously an electron has a negative fundamental charge and a proton has a positive fundamental charge. Now, due to the size of the fundamental charge, the coulomb is a very, very big unit. So we would often refer to charge in either of these prefixes, milli, micro, or nano. So when we are referring to a number, for example, 7 microcoulombs, that basically just means that it can be rewritten as 7 times 10 to the power of minus 6 coulombs. And the reason for that is because a coulomb of charge is such a big quantity, we often have to use these prefixes when talking about charges in everyday life. Now, it is possible for us to determine the number of fundamental charges that make up an amount of charge. So if we have an object that, say, has a charge of 3 coulombs, we can be asked to determine how many fundamental charges that contains, and we would say that the number of fundamental charges is equal to the total charge divided by the fundamental charge. Total charge here is given as 3 coulombs. Fundamental charge we know is always 1.6 times 10 to the negative 19. And what that tells us is that in a 3 Coulomb charge, there are 1.875 times 10 to the power of 19 fundamental charges, or in this case, because it's positively charged, protons present. As we can see, this is a very big number, so we are often going to use scientific notation when dealing with these charges. Then finally, it's important to note that since charge can only come in the form of protons and electrons, when there is an excess of one or the other, when there is an excess of electrons, an excess of negative charge, we say the object is negatively charged. When there is an excess of protons, we say the object is positively charged. However, protons, since they are inside the nucleus of the atom, they are never able to move. So whenever we talk about the transfer of charge, we are always going to be talking about electrons that are able to move, and the electrons would obviously always move from the more negative charge to the less negative charge because they are attracted to the positive charges in another object. The principle of conservation of charge states that the total amount of charge in an isolated system remains constant, and one way that we show that is with something called charge sharing, where we have two charged objects that are initially separate from each other. So here we have object A with a charge of 7 coulombs and object B with a charge of -3 coulombs. And so what we're saying is the isolated system is the system that contains these two objects. And so what we can see here is that we can see that the total amount of charge here is equal to 7 coulombs plus the -3 coulombs. The total amount of charge in this system is 4 coulombs. What would then happen is these two objects are then brought into contact with each other, where they touch each other, and as a result of this contact they are able to share charge. So what we find here is that at this point we still have the total amount of charge 7 coulombs plus -3 coulombs. We still have 4 coulombs of charge in the system, and then these objects are then separated once again. Still our isolated system only contains these two objects, and the question here would ask what the charge is on each of these objects. And so what we have is called charge sharing, and we can calculate the new charge on object A by realizing that it is going to be equal to the initial charge of A plus the initial charge of B, so the total charge in the system divided equally amongst, in this case, the two objects. Obviously it's possible for there to be 3 objects, and then you would divide by 3. So in this case it's going to be the 7 coulombs of A plus the -3 coulombs of B divided by 2, which gives us 4 divided by 2, which tells us that the new charge on object A is equal to a charge of +2 coulombs, and it is also going to be the new charge on object B because the charge is shared equally. An extension of this question would be calculate the change in charge for any one of these objects, and we can say that the change in charge on object A is equal to the final charge of A minus the initial charge of A, and that tells us the final charge is 2, the initial charge was 7, and the change therefore was -5 coulombs. And as we can see, A went from having a charge of +7 to having a charge of +2, which clearly shows that it has lost 5 coulombs of charge. We can do the same for object B, where here we can calculate the change in charge of object B by subtracting the initial charge from the final charge, and the final charge here was 2, the initial charge was -3, the signs here are important, and we see that the change in charge here was +5 coulombs, which again makes sense because we went from -3 to +2. What's important to see here is that the change in charge is equal but opposite, because 5 coulombs of charge were transferred from one object to the other, and then we know that protons are unable to move. So the only charge that can ever be transferred is electrons, so it's always the electrons that are transferred because they are free to move. And as we can see, the electrons would go from this particle or the substance or the object with more negative charge towards the object with less negative charge. As we can see, B is negatively charged, therefore has an excess of electrons, and the electrons would therefore be transferred from B to A. We can calculate the number of electrons using the formula N is equal to Q over QE, where we know that QE is the fundamental charge. And we can see here that our 5 coulombs of charge that were transferred divided by our fundamental charge, which is given as 1.6 times 10 to the negative 19. That is the charge on a single proton or on a single electron. And putting that into a calculator gives us a value of 3.125 times 10 to the power of 19 electrons that were transferred from B to A. Electrons are always transferred from the more negative to the less negative object. And then, as we can see here, the total amount of charge in this system has remained the same. Coulombs law states that the magnitude of the electrostatic force exerted by one point charge on another is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between their centers. So what this tells us is, for two objects that are separated by a certain distance, there is going to be an electrostatic force that exists between them, and that force is directly proportional to the magnitude of those charges, basically saying that the bigger the charges are, the bigger the forces are, which shows on that force versus magnitude or product of charges graph. What it also says is that it is inversely proportional to the square of the distance between these objects, basically saying that the further apart these objects are or become, the smaller the force gets, and it is an inverse proportion, meaning that that changes exponentially. And then finally what we can see is what's called the inverse square law, is the relationship between force and 1 over the distance between their centers squared, and we see that that is a direct proportion. This can also, these graphs can also be written as force is directly proportional to the product of the magnitude of the charges, and it is also directly proportional to the inverse square law, 1 over the distance between their centers squared. And in order to convert that into our Coulombs law equation, all that we need to do is add a constant. That constant here is K, and that tells us that the force between two charged objects is equal to the product of their charges multiplied by K divided by the distance between their centers squared, where K is a universal constant of 9 times 10 to the 9 Newton meters squared per Coulomb squared. So we can now use this formula to calculate the force that exists between these two charged objects, starting with Coulomb's law, which tells us F is equal to KQ1 Q2 over R squared. K is given to us and is a constant of 9 times 10 to the 9. Q1 is 3 coulombs, Q2 is 5 coulombs, and the distance between them is 2, and that must be squared. And that tells us that the force between these two objects is 3.375 times 10 to the power of 10 newtons. Now we know that this force is a vector, which means that it must have direction, and the direction is determined by the sign of these charges. Here we can see that these two objects are oppositely charged, which means that this force would be toward each other. Obviously, if the objects have like charges, the force would be away from each other. And then something that commonly confuses people is that sometimes you would be asked to determine the force that B exerts on A, in which case the magnitude would remain the same. But in this case, B is pulling A towards the right. So there you would write the force that exists by B on A would be 3.375 times 10 to the power of 10 newtons, and that is then towards B. And similarly, if asked to calculate the force that A exerts on B, it would be the same magnitude by Newton's third law, 3.375 times 10 to the 10 newtons, except that now that force would be towards A. So it's important to pay attention to how the question is asked. If the question is, what is the force between these two objects, it would either be toward each other or away from each other. if the force is what force is B exerting on A, then we would say that the force is towards B or away from B. And if the force asks what is the force that A exerts on B, we would then state that it is either towards A or away from A. An electric field is a region in space in which an electric charge experiences a force. And what this tells us is that around every charged object, there is a region in space in which another charge would experience a force, and we would show that region with the use of field lines. Field lines give us an indication of field strength around a charged object or in an area, where we can see that field lines, where they are closer together, represent a stronger electric field, and as they get further apart, the electric field gets weaker. It's important to note, field lines must always be drawn perpendicular to the surface on which they originate, and field lines may never cross or touch because that would suggest that there are two different electric fields at a specific point. The next important thing to note is that every electric field has a direction that we define as the direction in which a positive test charge would move if placed at that point. So I'm drawing the electric field around a positively charged object, which suggests that if I place the positive test charge at this point, it would be repelled away. And so we show that a positive test charge would be repelled away from this charge, and we say that these field lines are directed radially outward. Now, that is how we determine the electric field direction. What is also important here is to determine the electric field strength. And the symbol for electric field is uppercase E, and what it tells us is that the electric field is directly proportional to the size of the charge. Obviously, a bigger charge here would create a stronger electric field around it. We still have our constant here that we had in Coulombs Law, and what we can see is that the field lines get further and further apart the further away we move from this object, and so the inverse square law applies here, and that tells us that the electric field around an object is equal to the product of this constant k multiplied by that charge divided by the distance at which we are measuring that field squared. So as an example, we could calculate the electric field at this point P, and because every single charged object creates an electric field, it is not necessary for there to be a charge placed at P. We can determine what the electric field strength is at that point, and we know that the direction would still be radially outward. From this formula for electric field strength, we can see that the electric field strength is inversely proportional to the distance between these two, and what we can see is that that is not only inverse, but it is also an exponential. So we can see here from our inverse square law that the electric field strength is directly proportional to 1 over the distance squared, and as we can see, the charge that is producing the electric field that is in this formula has a direct proportion to electric field strength, which is shown on a graph like that. It is important to be able to draw the electric field around a positively charged object, similarly around a negatively charged object where the field pattern remains exactly the same. The difference here now is that a positive test charge placed in this field would move towards that negatively charged object, so the arrows point in a different direction. All the rules for field lines still apply. What's important to note here as well is that an object that has a bigger charge, so if this is -1 coulombs and this object is -2 coulombs, we would illustrate that by drawing twice as many field lines, because we know the number of field lines is representative of the field strength at that point. So we can show that a stronger charge or a bigger charge results in a stronger electric field, and it's important to draw all of the arrows as every field line must have a direction. And finally, what's important is to be able to draw the electric field pattern between two objects, between two like charges. Where we have two positively charged objects, we can show that those field lines essentially repel each other, as we have shown here. Once again, very important that these field lines never cross or touch. The field lines must all have all of the necessary arrows to indicate the direction in which the field points at that specific point. And again, these field lines should not cross or touch each other. Obviously, the electric field drawn between two negative charges would look exactly the same, only that the arrows would point in opposite directions. And then finally, to draw the electric field pattern between two oppositely charged objects, we would show the direction in which a positive charge would move if placed at that point. And what we can see here is that the electric field lines are directed from the positive charge towards the negative charge. The electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. And the formula for electric field at a point can be derived from a combination of Coulombs Law and our original electric field formula, where Coulombs Law explained to us that the force between any two charges, Q1 and Q2, is directly proportional to the magnitude of those charges and inversely proportional to the distance of separation squared. And our original formula for electric field tells us that the electric field around an object is directly proportional to the magnitude of that charge and inversely proportional to the distance of separation. Now, what we can see in writing Coulombs Law is that Coulombs Law contains the expression for the electric field around one of those charges. As we can see here, the first part of Coulombs Law tells us that the force is equal to K times Q1 divided by R squared, which we can rewrite just to make it a bit more visible, times Q2. And what this tells us is that the force experienced between two charges is equal to the product of the electric field. As we can see, this is the expression for the electric field around one of the charges multiplied by the charge experiencing that force, or this can then be rewritten as E is equal to F over Q. As we can see, the units for this electric field would then very clearly be newtons divided by Coulomb, or we'd say that as newtons per Coulomb. It is now very important to be able to distinguish between which electric field formula to use at which time. And very simply, this electric field formula is used when you are given the charge that is creating the electric field. It is the charge that is making the electric field around it. We remember that the electric field is the region in space around a charged object. And so when you are given the magnitude of that charge, this charge over here, we would use this formula to determine the electric field at an area or in a space or at a distance from that object. When instead you are given the charge that is experiencing a force, when you're given a charge that is experiencing a force, then you would use this new formula which says that E is equal to F over Q, where this Q is the charge that experiences that force. So once again, this formula is used when you are given the charge creating the electric field. This formula is used when you are given the charge experiencing the electric field. What is important to understand here is the direction of an electric field, and we know that the direction of an electric field is the direction in which a positive charge would move when placed in that field. So when we are told that a positive charge placed at this point experiences a force to the right, then what that tells us is that the electric field is directed towards the right. When we are told that a positive charge experiences a force at some strange angle, then we know that that is the direction of that electric field. And then sometimes, as an alternative, we are given something where we are told that a negative charge, experiences a force to the left at this point, which then tells us that our electric field is directed to the right at that point. So important to understand the difference between an electric field, which is the entire region in space around a charged object where another object would experience a force, and the electric field at a specific point, which refers to the force that is experienced by a charge placed at that point, and again the emphasis there being on a positive charge placed at that point. A very common electric field calculation question would look something like this, where you are given a certain charge, in this case -5 times 10 to the -8 coulombs, and asked to calculate the electric field at a point P, a certain distance away. In this example, we are going to say 5 meters away. Now, since this is the charge that is creating the electric field, we are going to use the formula electric field is equal to kq over r squared, because this charge in this formula refers to the charge creating the electric field. K, we know, is our constant, and Q is given to us as 5 times 10 to the -8 coulombs, and the distance between them measured in meters is 5 squared. So this tells us then that the electric field at this point is 18 newtons per coulomb. And what's important here is being able to define the direction. And we know that electric field direction is always defined as the direction in which a positive test charge would move if placed at this point. And we can see here that a positive test charge would very clearly be attracted towards this charge, and so we say that the direction of this field is towards the point charge, or the charge if it was given a name, point A, etc. So we have now calculated the electric field at a point 5 meters away from this charge. Important to note here that by directing it as towards this point charge, instead of saying upward, this will always be true. So if the point P is drawn here 5 meters away, the direction would still be correct as it is still towards that point charge. This question would normally follow on to say, calculate the force F experienced by a 3 picocoulomb charge if placed at point P. And so, since we know that we have a formula that relates the electric field strength to the charge experiencing the force, so note here that this is the charge that is experiencing the force. The electric field we've already calculated at a distance of 5 meters away, and so we can say the electric field strength is 18, and the charge was given to us as 3 picocoulombs, which we know means 3 times 10 to the -12 coulombs. And this then tells us that the force experienced is 5.4 times 10 to the -11 newtons. And then finally the direction. This is a positive charge, and so this positive charge would be attracted towards that point charge once again. Again, I prefer to always give the direction in reference to the charge creating that electric field, so that this is true no matter which direction you look at it from, whereas if you wrote it as upwards, it would only be true when looking at it in this direction. And so we say the electric field is towards this point charge. Once we have an understanding for the electric field at a point, it's important to understand the idea of the net electric field at a point. So a common question would look something like this, where you're given two charges and some point either in between them or on one side of those charges, and asked to calculate the net electric field at that point. And just like we would calculate the net force, all that we need to do here is see that the net electric field is just going to be the sum of the electric fields at that point. So what we can see here is there are two electric fields that are experienced at this point. The first being the electric field as a result of this first charge. Let's call it charge A and this called charge B. And as we can see, if we were to place a positive charge at this point, we would see that the electric field as a result of charge A would be towards the left. And very clearly we can see here that the electric field as a result of charge B would be towards the right. So we can immediately write down our expression for the net electric field by saying our net electric field at point P is going to be equal to the electric field as a result of B minus the electric field as a result of A. Once again, we must subtract them because they are vectors acting in opposite directions. From here, we simply calculate the electric field as a result of each of these two charges. So the electric field as a result of A at point Q is equal to KQA over R squared, since A is creating the electric field. That is our constant 9 times 10 to the 9 multiplied by 7 microcoulombs, which we know is 10 to the negative 6, over the distance between them squared, that is 35 millimeters, 35 times 10 to the negative 3 squared, which gives us an electric field as a result of A of 5.14 times 10 to the 7, measured in newtons per coulomb. And what we can see is that is towards A. The electric field is the direction that a positive charge would move if placed at that point, and here that is towards A. We can then do the same for charge B and calculate the electric field as a result of B, which is now KQB over R squared. K, once again, our constant. The charge on B given as 3 microcoulombs, micro being 10 to the minus 6, and the distance here given as 18 millimeters, 18 times 10 to the negative 3 squared, which means that our electric field as a result of B would then be 8.33 times 10 to the negative 7, once again measured in newtons per coulomb, and a positive charge here would experience a force towards B. So we can now clearly see why we have subtracted these, because the forces are in opposite directions, so the electric fields are in opposite direction, and we can now calculate our net electric field as 8.33 times 10 to the 7, apologies, that is times 10 to the 7, 8.33 times 10 to the 7 minus 5.14 times 10 to the 7, which gives us a net electric field of 3.19 times 10 to the 7 newtons per coulomb. And as we can see, this is towards the right, or more accurately, towards charge B. So once again, your free body diagram, very important here, where you're identifying the direction of each electric field so you can very easily write an expression for your net electric field.